Okay, good morning everyone. Good morning. Good morning. Welcome back from spring break. Let's get back to reality. All right. So I'm going to start off with a couple of problems today, okay, just to keep the pace a little gentle. This will probably refresh our memories on what some of us have been talking about. And hopefully, in the next few lectures, we are going to wrap up radiation heat transfer. Okay? And then we will get to convection heat transfer. All right. Very brief recap of certain things that you might have seen before. I'm just going to write it down. We're not going to explicitly write everything out. Okay? So we looked at emissivities. Three of them that we have seen so far. One is the spectral directional emissivity, which is epsilon lambda theta and phi. This is the ratio of the intensity of the emitted radiation to the intensity of a perfect body which is emitting radiant energy at the same temperature. Okay, so this is I lambda comma E by lambda comma B, lambda and T. Lambda comma B is the intensity of a perfect or an ideal body which comes from the Planck distribution. Okay. Then we looked at spectral emissivity, epsilon lambda, function of lambda, which means that if you have the subscript lambda, the integration is over all the angles. So this is integral 0 to 2 pi, pi by 2, lambda, sine theta, cos theta, d theta, d phi, divided by the same thing, but instead of I lambda comma E, it's I lambda comma B. This is spectral emissivity. Spectral meaning it's a function of wavelength. And then two more actually. One is the directional emissivity, which is the problem that we're going to solve today. The day we met before spring break, which was Friday last week, I solved a problem using epsilon lambda. Okay. Today we're going to solve a problem using epsilon theta, and then I'm going to go into absorptivities and so on. So epsilon theta, by definition, is mostly a function only of theta. Okay, it's supposed to be independent compared to the angle phi. Once again, these are all surface parameters or surface properties, and these are experimentally okay from spectroscopic studies. By definition, this is 0 to infinity lambda comma E by lambda comma B d lambda So once again, as I mentioned, if the subscript is theta here, then the integration is over the wavelengths. If the subscript is the wavelength, The integration is over all the solid angles. Okay, that's a way to remember these. The presence of one precludes the absence of the other. Then the last one is epsilon t. This is purely a function of temperature. Okay. This is a triple integral. It has no subscripts, which means it's integrated over everything. So this is 0 to 2 pi, pi by 2, sin theta, cos theta, d theta, d phi, d lambda, by the same thing. Instead of writing it, we typically write it as E suffix b. E by E suffix b. Typically epsilon lambda is also written as, I'm going to sneak it in here, E lambda divided by E lambda comma b, okay, and epsilon theta is written as I lambda by, or IE by IB. And as you know, E suffix b is sigma t to the power 4. Spectral, directional. Spectral. Directional only, total. In all problems, our aim is to calculate this guy, but in most problems it is difficult to calculate it because this is a function of multiple things. It's a function of wavelength, it's a function of temperature, it's a function of angles. And so we either need information regarding the functional dependence on angle or the functional dependence on wavelength in order to calculate epsilon. Okay? And that's our next problem. I'm given the following directional emissivity for the surface at 500 Kelvin. The directional emissivity is given as follows. Theta in degrees. Epsilon theta, these are dimensionless, okay? Emissivities and absorptivities and so on. Typical range goes from 0 to pi by 2, right? So 0 to 90 degrees. If we had an ideal body is a diffuse body, which means that none of its parameters are dependent on direction. Which implies that if I drew epsilon theta for an ideal body, it should be having a value of 1. This is for an ideal body. For an ideal surface. Okay. What I'm saying is, okay, for the surface that we have, this is the real surface. The directional emissivity is given as the following. It's equal to 0.9 from 0 to 75 degrees. And it's 0 after that. Okay, so 0 to 75. That's the so this is for the real surface. So there is a certain drop off that happens once you go beyond this 75 degrees. Okay? What are the things we need to obtain? epsilon and E for the surface. And this is for the real surface. Alright, these are all just direct applications of the formula. There is not much thinking involved. The thinking is in the actual development of the experiments, but that falls beyond the scope of this class. The spectroscopic experiments that are designed to measure these parameters, okay? A typical class on radiative heat transfer will go over those things. So what we're going to do is we're going to directly first start off with this guy, epsilon theta. Okay, so by definition, epsilon theta is integral from 0 to infinity. This is I lambda comma p d lambda divided by lambda comma b d lambda. We are asked to find epsilon t. Epsilon as a function of temperature. And how do we do this is, I once again recall the definition of epsilon. But I write it in such a way that I'm able to isolate certain terms and then substitute for epsilon theta. Okay, so here is how we do it. You see that the integral is from 0 to infinity, so when I write epsilon, I'm going to isolate that integral and leave the rest. So this is 0 to 2 pi, 0 to pi by 2, 0 to infinity, lambda e, d lambda, sine theta, cos theta, divided by 0 to 2 pi, pi by 2, integral 0 to infinity, lambda b, lambda, d theta d phi. These are all just basically again from definitions. What I'm going to do is, I'm going to say that, okay, hey, this guy is actually that. And so I'm going to substitute for integral 0 to infinity I of lambda comma e as epsilon theta multiplied by this integral here. Does this make sense to everybody? Okay, just cross multiplication. Okay, so if I do that, I have epsilon is now 0 to 2 pi, pi by 2, epsilon theta 0 to infinity, lambda comma b, d lambda, sine theta, cos theta, d theta d phi, which is coming from the substitution that we have made by cross multiplying that first term there, and then something similar in the denominator. Is everybody clear on what I'm doing here? This comes from substitution, okay, directly from the first big term there. This is just a repetition of what I've written down there, which is in fact a repetition of what I've written down there, up there. And now you can obviously see that epsilon theta is independent of lambda, so this and that can be cancelled off. And you can do this precisely because the ideal body is a diffuse body. It's a diffuse surface. It's independent of theta. Okay? I cannot do the following. I cannot come and cancel off things like that. Okay? So please don't do that. Okay, so we have the following now. This is equal to, what's this? Epsilon theta is a function only of theta, it's not a function of phi. So I don't need to integrate over epsilon theta over phi. So just 0 to 2 pi d phi is just going to give me 2 pi. This is 2 pi. Integral from 0 to pi by 2. Epsilon theta, sine theta, cos theta, d theta d phi. Integral 0 to pi by 2, 0 to 2 pi sine theta cos theta d theta d phi. We have done this integral many times and it's equal to pi steradians. Factor of pi cancels off. And now all I have to do is the following. Is 2, and that remains. And I'm just going to split this integral from 0 to 75 degrees, which is 5 pi by 12, and then from 75 degrees to 90 degrees. Epsilon theta is defined in different ways. So this is 0 to 5 by 12, sine theta, cos theta. That's just the d theta there. Plus degrees to 90 degrees, epsilon theta is 0, so if you want, you can call this as epsilon theta 1, epsilon theta 2. Epsilon theta 1 is 0.9 in that range, epsilon theta 2 is 0, so that second integral drops off. And so I'm left with integral sine theta cos theta, epsilon theta 1, which is a constant in this range, so that's 0.9. So this is 2 times epsilon theta 1, 0 to 5 pi by 12. Sine theta cos theta, you can typically write it as sine 2 theta and a factor of half. So this is half times sine 2 theta d theta. As you know, you can plug it into Wolfram or MATLAB or do it by hand. Either is fine. Calculate. It will end up being .84. Where epsilon theta 1 is 0.9. And if I have to calculate the total emissive flux or the total emissive power, it is just sigma times epsilon times t to the power 4. So epsilon is E by E suffix b, so E is EB times epsilon. Which is sigma epsilon t to the power 4. You can perform the substitution. Sigma is your Stefan Boltzmann constant. You're going to get that person known to you very well in the next couple of lectures. We're going to solve some numerical problems. T is 500 Kelvin. Epsilon is 0.84. Before I move on to the next problem, are there any questions? And I still want to talk a little bit about this problem. So one thing I want to point out is the following. In many problems, you can, oh, this question.
Why does the epsilon stay to 2?
Oh, because it's 0 here. So from 75 to 90, it's 0. And this is 0.9. So one thing I want to point out is for many surfaces, you can define something called as a normal emissivity, which is the directional emissivity at theta is equal to 0 degrees. Okay? So if I look at this problem here, directional emissivity is epsilon theta. At theta is equal to 0 degrees, the directional emissivity is 0.9. Also notice, the total emissivity, after doing all this thingamajig here, is 0.84. 0.84, 0.9, if you close one eye, they are pretty much the same. So for a lot of problems, if you know what type of a surface they are, and if they are non-conductors, ceramic surfaces and so on, you can pretty much say that the normal emissivity, which is epsilon theta at theta is equal to 0, is equal to the total emissivity. And you don't need to perform any extensive calculations, one can directly calculate the radiative flux and so on. Okay, so I'll write this down. Normal emissivity typically denoted as epsilon n, and this is the same as epsilon theta at theta is equal to 0 degrees. And for many non-conducting surfaces, so in our problem, epsilon n is 0.9, as you can see from the figure there. Okay, when theta is equal to 0, epsilon theta is 0.9, so this is epsilon n. And epsilon, which is the total emissivity, is 0.84, which is approximately equal to epsilon n. And so this is a very reasonable approximation for a lot of non-conducting surfaces. For non-conductors, we can mostly say that not true for conductors, they are a little more devious, but non-conductors are fine. Okay. In this problem, next problem, yes, question.
So pretty much every time we see a non-conductor,
That's a reasonable
just
approach.
go for that.
Absolutely, absolutely. Let's just go for it. And I think I kind of explained the reasoning last time, is that if you have typically conducting surfaces, metals and so on, they're very shiny, which means that their surface roughness is very small compared to the roughness of maybe a non-conductor. And so there is a greater chance of emissive power in a non-conducting surface versus a conducting surface, and this remains constant over a longer range of the angle theta. Okay, so that's one reason why you can have. Okay, so the next problem is on absorptivity. So we did emissivity, we are now looking at absorptivity. If you combine them together, you get total radiative flux, which is what we want really. We still have one last giant leap to make, which is called Kirchhoff's laws of radiation, which will in fact tell us when is epsilon equal to alpha. You remember alpha was absorptivity. We will eventually come to that conclusion that for certain surfaces, all of this thing that we've done is a waste of time. Epsilon is equal to alpha, you just move on. But to get there, we need to know all these things. Of course, it's not a waste of time. This is true for most real surfaces. You have to go through all these hoops to find epsilon and alpha. And you're going to see this in this problem. So you're given the spectral irradiation a surface which is at 1000 Kelvin. Okay? Irradiation is G, capital G, so just a note. Is G, which is in watts per meter square. This is the same unit as the emissive flux or the emissive power. Which is capital E, which is also watts per meter square. We have the spectral emissive power or the spectral emissive flux, whose counterpart in irradiation is the spectral irradiation. It's a spectral irradiation is G subscript lambda, okay, and so its units are going to be in watts per meter square, micrometers. And if I take the spectral irradiation and integrate it over all the wavelengths, I get the total irradiation, capital G. This counterpart in terms of emissive flux and so on is the spectral emissive power or flux, which is E lambda, which is also the same units. All right. So I'm given the following graphs. Okay. So G lambda 0, 2, 4, 6. This is G lambda, and this is 5000. Watts per meter square micrometer, that's a value there. Okay, so this line here is 5000. So between 0 and 2, there's a triangular distribution. Between 2 and 4, there's a rectangle. And then between 4 and 6, there's once again a triangle that drops down. Okay. At all other wavelengths, G lambda is 0, beyond 6 micrometers. This is one thing that's given. I'm also given the absorptivity, the spectral absorptivity as a whole, right? This is alpha lambda, I'll write it out, as a function of lambda. Between 0 and 2, it's 0. And it's a 0.6 after that, so this is 0, 2, 4, and so on, right? After that it just goes off at 0.6. So epsilon alpha lambda is the spectral absorptivity. It is defined as the following. Like we had I lambda comma E for emissivity and so on, we have the intensity of the incident radiation when we are talking about absorptivity and all these characteristics. And essentially we are comparing how much is absorbed versus how much is incident on me. Okay? So this is going to be integral from 0 to 2 pi, 0 to pi by 2. I'm first going to write the denominator, 0 to 2 pi, 0 to pi by 2, lambda comma I. Please notice that little I means this is the intensity of the incident radiation. This has nothing to do with a perfect body or an ideal body. There is no subscript little b there. That will happen once we study Kirchhoff's laws. Later on, okay, in the next lecture. At this point in time, this is just the intensity of the radiant energy that is coming from surrounding sources, which need not be ideal bodies. Okay? And this is going to be lambda theta phi sine theta cos theta d theta d phi. This is the total incident radiation, out of which only a portion is absorbed. So in the numerator, I'm going to have the following: I lambda comma abs, whatever is the fraction of this incident radiation that is absorbed by the real body. Function once again of all of these: sine theta, cos theta, d theta, d phi. Excuse me. And this ratio is called as G lambda absorbed by G lambda. Look at the similarities. Okay, so right on the top panel there you have epsilon lambda. Right down here you have alpha lambda. They are very similar looking creatures. The only difference being, in the denominator for epsilon, I am always comparing the emissivity of any real surface to that of an ideal surface. I don't have that right to do it for absorptivity because I am not sure if the surrounding surface that is sending me energy is an ideal surface or not. Okay? But the methods look the same, the expressions look the same, and in fact I call the ratio as E lambda by E lambda comma B. And similarly, this is G lambda. If it's an ideal body, there will be G lambda comma B at some point. And G lambda comma absorbed is a portion of whatever that is incident on me that is absorbed by me. Okay? So this is the definition of spectral absorptivity. What do we need to find in this problem? Obtain alpha. Okay, which is the total absorptivity. And obtain G absorbed, G lambda absorbed. Of course, G lambda and G lambda comma absorbed, these are at particular wavelengths which are already given to us. So I have G lambda, this is given to me, so I don't need to find it. I need to find G lambda comma absorbed using this plot and that plot. And something else that I'll also specify is that G, which is the total irradiation, is the integral of G lambda over all the wavelengths. So note, and so G absorbed is nothing but the same thing with G lambda comma absorbed. Okay, now my question to you. Can somebody tell me how to find capital G using this plot? Yes. Find the area under this curve. It's as silly as that. How do I find G absorbed? To do that, I I have to first of all write G lambda comma absorbed as a function of lambda, but I know this guy, so here is how we do it. So first step is I draw the plot that I have. This is 0, 2, 4, and 6. This is G lambda. And that's 5,000 here. How do I find G lambda comma absorbed? Is essentially I take G lambda and I multiply it by alpha lambda, which is given to me here. You see that? So which means that from 0 to 2 micrometers, G lambda comma absorbed is essentially 0. Okay, so I'll write this down here. So G lambda absorbed by G lambda is alpha lambda, which means that lambda comma absorbed is alpha lambda times G lambda. Alpha lambda is 0 from 0 to 2 micrometers, so G lambda absorbed is 0. Then what do I see? I see that alpha lambda is 0.6 all the way from 2 to infinity. And all I have to do is just multiply this figure by a factor of 0.6 from 2 to infinity. So from 2 to 4, it's 0.6 times 5,000, which is 3,000. Does this make sense to everybody? Then what do I do? I know that I have to end at 0 here. So it does not really matter, I just go down in a linear fashion with a different slope. And this shaded figure now, if I take the area, is going to give me G absorbed. Okay, so this is G lambda versus lambda, and this figure is G lambda absorbed versus lambda. I want to make sure there are no questions on this. Can everybody let me know if you are okay with what we've done so far? I have those two plots. The first plot is G lambda versus lambda. I need to find G lambda comma absorbed. By the definition, this is just alpha times G over that particular wavelength range. From 0 to 2, alpha lambda is 0. From 2 to infinity, it is 0.6. But I don't need to go to infinity because after 6 micrometers, my spectral irradiation drops off to 0. So all I have to do is, from 2 to 4, it's going to be 0.6 times 5,000. And then from 4 to 6, the slope of this is going to be reduced by a factor of 0.6. Okay, so if the slope was 5,000 by 2, so that's 2,500 was the slope for this guy. This will be 1,500. That will be the slope of that. Okay, 2,500 times 0.6. So once I have those two, then we are pretty much good to go. And I want you to see the crux of the argument here. If I know these guys, then I can calculate everything. If I know alpha lambda, or if I know epsilon lambda, or if I know epsilon theta, likewise if I know alpha theta and so on, if I know those things, I can calculate everything. I can calculate the emissivity, I can calculate the absorptivity. If I know the emissivity and absorptivity, I can calculate the net radiative flux. The big issue is, okay, how do you get these values? This is obtained from experiments. The bigger issue is, okay, in terms of irradiation, I don't know these creatures. We're going to make some approximations in the next lecture and say that under certain circumstances, if the surroundings are diffuse, I can equate this to the radiation coming from an ideal surface. And when are those valid? Okay, those are things that we're going to see. Okay, so G, area under G lambda versus lambda curve. That's easy, so that's two triangles and then one rectangle. So this is 2 times half times 5,000 plus 2 times 5,000. I just wrote out the units to make you see that this is micrometers, this is watts per meter square micrometer, so I end up getting watts per meter square, which is the unit for irradiation. This is 10,000, this is 2 times 5,000, so that's 20,000. Watts per meter square. This is capital G. By the same stretch of imagination, what is G absorbed? G absorbed, if you look at that integral there, that's integral 0 to infinity, G lambda comma absorbed d lambda, or the area under the G lambda comma absorbed is lambda curve. Which is one rectangle and one triangle. So this is half times 2 times 3,000 plus 3,000 times half times 2. So that's 6,000. So it has to be 3,000 times 2, not half. So 9,000. Watts per meter square. I have G absorbed. What's alpha? The ratio of these two. Okay, so alpha is G absorbed divided by capital G. And G absorbed is 9,000, capital G is 20,000. .45. Questions before I go to the next part of this problem? I have 10 more minutes left. The plots are given the information, calculate the remaining things. Okay? Now, same problem, have all those values, and let us say, for the sake of having a thought experiment, let us say that somehow we performed some experiments and we figured out that epsilon lambda is the same as alpha lambda for this problem. Okay, so same problem. Say epsilon lambda is equal to alpha lambda. Calculate epsilon then. Surface temperature is 1000 Kelvin. So obtain E. For the surface, because we're doing the same problem, alpha and G are the same as before. and for all these emissive characteristics, obtain the net radiative flux, which is what we want to do for each and every problem from now on. We have all the absorptivity characteristics given to us, some information on the emissivity, obtain the net radiative flux. Obtain Q double prime radiation, which is in watts per meter square. So epsilon lambda is the same as alpha lambda, so the same plot. These are all lambdas. This is 0.6, 0, 2, 4, and so on. If I know epsilon lambda, we did a problem of this sort in the previous lecture. I'll be posting those screenshots, by the way, today. How do I calculate epsilon? Okay, so by definition, epsilon lambda, first of all, is E lambda by E lambda comma b. Now you can use the integral form and so on. So epsilon, which is the total emissivity, different from the absorptivity, okay? Epsilon of t is integral 0 to infinity E lambda d lambda, integral 0 to infinity lambda comma b d lambda. Does this make sense to everybody? This is the basic definition. I did not write the integrals. We had them written in the first panel right out there. Epsilon t is nothing but taking all of those over the entire range of wavelengths and then integrating the spectral emissive power. Substitute. So this is integral from 0 to infinity. Instead of E lambda, I'm going to substitute epsilon lambda times E lambda comma b. D lambda divided by 0 to infinity lambda comma b d lambda. Epsilon lambda is 0 from 0 to 2 micrometers and 0.6 thereof on. So I just split the first integral into 2 on the numerator. So epsilon is 0 to 2 epsilon lambda lambda comma b d lambda by 0 to infinity lambda comma b d lambda plus 2 micrometers to infinity micrometers epsilon lambda lambda comma b d lambda by total emissive power. So two integrals or two ratios here. What's the first one equal to? 0. Why is it 0? It's because from 0 to 2 micrometers, what's the value of epsilon lambda? It's 0. The second one, epsilon lambda is a constant, so I can pull it out and write it as 0.6. We'll complete this in a couple of minutes. Integral from 2 to infinity